My name is Valerie Bernstein. I'm a graduate student at the University of Colorado Boulder, working with Doctors Marcin Polinsky and Dolores Knipp. And today I'll be talking about uncertainty in modeling atmospheric drag near the oxygen-to-helium transition. And to introduce why atmospheric drag is so important, this animation is showing how the number of satellites and debris objects orbiting Earth, especially in low Earth orbit, has been increasing over time. So we need to be able to model atmospheric drag for precise orbit determination and collision risk analysis for these satellites. So first, let's make sure we're familiar with the concept of atmospheric drag or satellite drag. So atmospheric drag is the perturbing force of the Earth's atmosphere on near-Earth satellites. And here I'm just showing a not-to-scale cartoon of how the drag force can disrupt a nominal satellite orbit. So I mentioned in my title that I would be talking about atmospheric drag near the oxygen-to-helium transition. So while Earth's atmosphere can extend all the way to 1,000 kilometers in altitude, the O to HE transition typically exists around 500 to 600 kilometers. This orbital region is interesting for a bunch of reasons. In an operational sense, this is a regime which is growing increasingly crowded with satellites. It's a popular orbital regime for CubeSats as well as for large constellations of communication satellites in the near future, as we can see an example of here in the video on the right. Also, the SpaceX Starlink communication satellite constellation operates at 550 kilometers. So we're talking about tens of thousands of satellites launched to this altitude in the next few years. And the image on the left here is showing a partial visualization of this. From an atmospheric dynamics perspective, this is also an important region in the sense that we start to see major composition changes where helium increases and oxygen decreases. And helium becomes particularly important and abundant at these altitudes during solar minimum when you've got the winter helium bulge. So let's talk a little bit more about how we model atmospheric drag. This is the atmospheric drag force. The parameters that we're going to focus on today are the drag coefficient and the atmospheric mass density, since these have kind of the most uncertainty. So the drag coefficient in a physical sense represents the energy and momentum exchange between the atmospheric gas molecules and the satellite surface, while the mass density is most important for conjunction analysis. And I just want to talk briefly about how we can model drag coefficients through gas surface interactions. So one thing that's important to get right in these interactions is the nature of the scattering of the gas molecules when they hit the satellite surface. So different scattering scenarios for atmospheric gas molecules colliding with the surface are shown in the right figure, where we have an incident particle coming in and hitting the surface. So specular scattering is when the angle of incidence equals the angle of reflection. Diffuse scattering is when the angle of when the incident molecule is remitted in a random direction. And quasi-specular scattering is sort of a middle ground between the previous two. So the scattering lobe characterizes the angular probability distribution of the behavior of reflected molecules. So a narrower lobe means that the molecule is likely to scatter within a smaller range of reflected angles. So for modeling gas surface collisions, the change in energy and momentum of the incident molecules determines the characteristics of the reflected molecules. The change in momentum is described by the momentum accommodation, and the energy accommodation describes the amount of energy transferred in the collision based on the degree of temperature equilibrium between the molecule and the surface at reemission. And so I won't go into too much detail about the accommodation coefficients, but I will say that the level of momentum accommodation is related to the angular distribution of the reflected particles, and the amount of energy transferred determines the velocity of the reflected molecules. And so in general, larger momentum and energy accommodation leads to more diffusive scattering and smaller reflected velocities. And smaller momentum and energy accommodation coefficients yield more specular scattering, which leads to typically increased drag and larger drag coefficients. And I want to talk a little bit about what laboratory experiments and satellite observations have taught us about the nature of scattering in gas surface interactions, as well as the questions that we still have. So in general, lab experiments show that surface contamination plays a role in the scattering. And so by contaminated, I mean that the surface is covered in a layer of adsorbed molecules, causing the scattering to be more diffuse-like. So for cleaner surfaces in the lab, scattering has been more quasi-specular here. At LEO altitudes, though, below 500 to 600 kilometers, the dominant constituent in the neutral atmosphere is atomic oxygen. And oxygen adsorbs on nearly all surfaces, so it's considered to be the major contaminant for satellite surfaces. And so below 200 kilometers, roughly, altitude, one satellite measurement of the scattering distribution exists, which indicates diffuse scattering. But scattering dynamics are uncertain at higher altitudes in the thermosphere, especially above 500 kilometers due to a lack of measurements, and also a hypothesized cleaner surfaces than at lower altitudes, since this is where we start to encounter the oxygen to helium transition region that I mentioned before. So this is really the research question. What are the appropriate scattering dynamics to put into drag coefficient models at these altitudes where oxygen is diminishing and surface absorption may be decreasing? So the way that we can test drag coefficient scattering models is by deriving densities from drag and making comparisons. So let's say we have drag measurements for a satellite. These can come from accelerometers on satellites in space or from mean motion differences from orbital tracking data, for example. Then we can plug in modeled CD values and back out atmospheric densities, assuming that all the other parameters are known, including the area, mass, and relative velocity of the satellite. And so in order to test the consistency of CD models, we can do multi-satellite comparisons of derived densities for satellites orbiting in nearly the same space environment. So we have our drag measurements. Let's say we have it for two different satellites, and we plug in CD modeled with diffuse scattering. And then we back out densities for those two different satellites to get rho I and rho J, assuming diffuse scattering in the CD. And so let's also say that satellite I has a log shape like the GRACE satellite, while satellite J has a compact near spherical shape. And so we include comparisons between satellites of different shapes to test the consistency of CD model scattering assumptions across different geometries. Then we normalize the derived densities by an atmospheric model. So since the atmospheric model bias is expected to be the same for both satellites orbiting in very similar orbital environments, we do this step so that we can compare analogous quantities for GRACE and the compact satellite while removing differences in densities due to the satellites not sampling identical altitudes. Then we can define our density discrepancy metric, delta R, as the difference between the measured to modeled derived density ratios for the two satellites. So we can do this method for different CD scattering models like diffuse, specular, and others. By defining delta R like this, we're trying to attribute derived density discrepancies to effects of the gas surface interaction assumptions in the CD model. And we make these comparisons between the GRACE satellite with the elongated shape and a bunch of compact satellites orbiting within a scale height of GRACE. And so the idea is that delta R should be 0 if the CD model assumptions are perfectly consistent for the different satellite shapes. So let's take a look at some of our density discrepancy results. Binned average delta R values organized by average atomic oxygen number density in the atmosphere as an indicator for atmospheric pressure are shown in both panels. The different colors represent results from different drag coefficient models, including one that assumed an oxygen-covered surface with diffuse scattering, one that assumed a clean surface, and one that assumed a surface that was partially covered with adsorbed oxygen. And so the top panel shows average density discrepancies from all of the compact satellites, while for the bottom panel, a subset of satellites was selected which showed limited sensitivity to atmospheric model error. And so we really try to validate our all satellite results with results from the smaller, robust set of satellites. And we can see that density discrepancies are largest in magnitude and have the largest variability for the low pressure, higher altitude conditions. And we can split this up even further to look at results associated with dayside local times on the left and nightside local times on the right separately. And so the format of these plots are the same as for the plot on the previous slide. And we can see again that at the lower atmospheric pressures, delta R deviates more from 0, especially on the day side here. So these plots indicate that density, discrepancy response, and sign are sensitive to atmospheric temperature, day side versus night side, and composition. And it's also important to note that all three of the CD models tend to perform poorly at the lower pressures. The model which assumes diffuse scattering, which is the green one here, may produce the largest density discrepancy magnitudes, but the other two models also deviate pretty significantly from zero. We also notice from these plots that at higher pressures, we see minimal differences between the three drag coefficient models within uncertainty of the analysis. Okay, so what are the big picture takeaways here? We are seeing that current drag coefficient models do not produce consistent drag coefficients for low pressure atmospheres. Then, since we rely on CD models for deriving density data sets and constructing and validating density models, these density data sets and models may be significantly misrepresented at low pressure altitudes above the oxygen to helium transition. And though more thorough analysis is needed to confirm this, we identified that tangential momentum accommodation is likely misrepresented in CD models, which leads to overestimates of CD by up to about 30% at these altitudes. And so this would mean that drag-deduced densities are underestimated by the same amount near and above that oxygen to helium transition region. So if you have any questions or want to chat more about this work, feel free to contact me via email. And thanks for watching.